Hello students of the world, welcome to Magnetic Fields number 6, Geomagnetism. Geomagnetism is the study of magnetism as recorded in rocks, and molten rocks can record the Earth's magnetic field at the time that they crystallize. So we're talking about volcanic rocks here, and so when a volcanic rock is erupted on the surface, it's all very hot and it starts to cool, and one of the earliest minerals to crystallize from that hot lava is a mineral called magnetite, and it forms little rod-like crystals that are, because it's an iron mineral, they align themselves to the Earth's magnetic field, and they're free to move in the molten rock. And they do that, they align themselves to the Earth's magnetic field much like little bar magnets, and then the rest of the lava crystallizes around them and they're locked in position. And so people have been going around for many years drilling out cores in these volcanic rocks. They take them back to their labs, they've scribed onto them their orientation relative to the Earth's magnetic field currently, and then they look at what the paleomagnetism was in that rock. In their lab they can work out what the orientation of the Earth's magnetic field was from that rock, and there's been this whole study of the changes of the Earth's magnetic field through time, geological record, and there's a long record of this, and it had been recorded that the Earth's magnetic field had been swapping through the geological record, so the Earth's magnetic field had been reversing. So there's this massive amount of information about the Earth's magnetic field, but what does that prove? Well, tie that in with our knowledge of where all the volcanoes were, and tie that in with our understanding of the distribution of earthquakes, which we've looked at before. People were starting to think that there's a bigger something else was happening here other than the current ideas that people were thinking about, and this is in the 1950s and 60s in terms of geology and geomagnetism and geophysics. And so it had all this massive amount of data, plus the depths of ocean, which people had known for hundreds of years. There's deep areas of the oceans, but there are also these long ridges that are relatively shallow. And if we take a transect between North America and Africa across the ocean, we can see that it gets deep, and then in this what's called mid-ocean ridge area, it gets shallow, and then it gets deep again. And that had been observed, and people had lots of ideas, but nothing was really satisfactory in terms of explaining it. And then one day a ship sailed across the ocean, and it towed behind it an instrument that measured the Earth's magnetic field. And it was just doing a magnetic survey. It wasn't doing anything particularly exciting with any other reasons. And what it found was that the volcanic rocks that are the ocean crust is striped. There were stripes in it, and these stripes, should happen again shortly, represent orientations of the Earth's magnetic field, and they observed these stripes in this data, and it got people thinking. And so what they saw is when they sailed across the ocean, here's the rock, this is the oceanic crust, in terms of the symmetry of the magnetic field. And so the white here represents normal polarity, so north is north and south is south, but the orange represented a reversal of the Earth's magnetic field. And so moving away from this ridge, there was a symmetry in the patterns of the reversals, and people had seen that the Earth's magnetic field had reversed quite regularly in these volcanic rocks. And that started people thinking as to what was happening on mid-ocean ridges. And so this was the explanation that they had for it, is volcanic rocks are coming up from the mantle and forming volcanic deposits, and those volcanic deposits, that as they form they record the Earth's magnetic field with the magnetite, and then this oceanic crust is moving that way, and this oceanic crust is moving that way, and so a whole lots and lots of oceanic crust. So this is older oceanic crust from younger oceanic crust. And in this period, the Earth's magnetic field had reversed, and then it had been normal. And so this suggested that oceanic crust is constantly being made at these mid-ocean ridges. And so that then got people thinking, well, if oceanic crust is then being made at mid-ocean ridges, it's got to be consumed. Or what's happening? You just can't keep making oceanic crust more and more and more and more and more. There's got to be some explanation for how we can make more oceanic crust. But back to the magnetic polarity, and so we can see here that the Earth's magnetic field has swapped fairly regularly. It's not like a nice sine wave, but there is a regularity to its reversals, and some reversals are short-lived and some are long-lived. But that's in the geological record. And so right now we are thinking that we're overdue for a reversal, but we don't know when it's going to happen. And so just another diagram showing the steps. Here's the orange laid down, this moves out to here, then there's some more stuff laid, and so you get these bands forming. And in terms of dating, so people sent down dredges and brought up some rocks. If the mid-ocean ridge is 0 million years old, then as you move away from the mid-ocean ridge, the rocks get older and older. So we've got 10 million years old here. And so then this oceanic crust here would be even older. So if the new ocean floor is being made in mid-ocean ridges, why isn't the Earth getting bigger? Is a question people asked at the time. Well, some people said, well, it is. The answer is an expanding Earth. And there were a lot of people that actually believed that the Earth started out small and had expanded. And this correlated with the fact that you could take something like the coastline of Africa and South America, and they fit pretty well together. So in terms of geology and fossils and everything, they must have been next to each other. And then if the Earth expanded, they were just moved apart. It explained a lot of things. It also explained why dinosaurs are big, and you can go to that page if you like, because the Earth was smaller. Must be true, because it's also on the web. There's actually a web page, expandingearth.org, so that must be true. It also explains why there's no old oceanic floor. If you sampled all the oceanic floor, the oldest oceanic floor is only 120 million years old. Nothing older. And this is the idea. It starts out small and blows up like a balloon, so the continents covered it all, and then the ocean floor is made and the continents are pushed apart. So that's pretty good. However, it was completely wrong. And all these scientists and people had been theorising on an idea, and there was actually a famous Tasmanian professor, I can't remember his name, but he worked in the geology department at UTAS, and for many, many, many years he was a major proponent of the expanding Earth theory. And when this plate tectonics came out in 1970s, it took many, many, many years for him to actually accept plate tectonics as a valid theory. He would be arguing against it. But now it's universally accepted. And so basically it is, and we've talked about this before, the Earth is made up of a whole series of plates. And in some areas of the plates you make new crust in the mid-ocean ridges, but old crust is consumed in what's called subduction zones. And that relates to all the distribution of all the volcanoes. So oceanic crust hits the side of a continent. Continent is a big, dense, floaty thing sitting on the mantle, and the plate goes down, melts, makes volcanoes, away you go. That was the theory in the 1970s. Where was the evidence? And this was the whole picture. New crust formed in the oceanic crust, being consumed, continents moving around the place. They can actually get new crust on the continents as well. But the evidence was there. People started looking for it. Here's the distribution of earthquakes underneath New Zealand, and you can see that they plunge down where the crust is getting down. So the earthquakes are actually happening as the oceanic crust is being broken and melted. And this is Japan. So this is the slab going down, and you can see here there's a little bit of slab left over that is just melting, and this is down at 600 kilometers into the mantle, and you're still getting earthquakes, and it's still making volcanoes up in this area up here. And this one is Japan again, and you can see there's lots of earthquakes. This is the oceanic slab going down, and there's earthquakes occurring on the top of the slab and the bottom of the slab as it's sliding its way into the mantle and starting to melt and forming all these volcanoes. And again, this is at 200 kilometers below the surface. So we can see this. Tonga earthquake was a good example of recording it. And this is the distribution of all the earthquakes, corresponds with plate tectonics. What am I trying to show here? It was one of the biggest earthquakes in history, I think, the Tongan earthquake a couple of years ago. And it happened up on the surface, but it was just part of a series of massive earthquakes that occur where the subduction zones occur. Australia doesn't have a subduction zone because we're sitting here in the middle of a plate, surrounded on the edges of our plate by subduction and mid-ocean ridges, but we only very rarely get big earthquakes. Alright, now part of plate tectonics is that the continents have been moving around, and they move around the surface of the earth at about the same rate that your fingernails grow. So every time you cut your fingernails, think that's how far Australia has moved north, basically. And because the Earth's been around for a long time, 4.5 billion years, the continents have moved and they've wandered. And so on the OneNote, I'll put this little video that shows the last 650 million years in 2 minutes of how Australia, and you can see where the continent of Australia has moved around the globe. Quite interesting. So that's enough of that. Next video will actually be doing some of the stuff that you really need to know, electromagnetism. So cheerio.